Yep. Say something.
Go for it.
Okay, thank you for coming to the first differential geometry and physics seminar. Today, our speaker is Moscrop, who will tell us about moduli for n equals 2 QFTs. Please.
Great. Thanks for the introduction. So, first of all, it's a great pleasure to be the first speaker in this seminar series, and drawing such a huge crowd of people. So I hope it keeps up in future weeks. So, when Saman and Max asked me to speak, they kind of wanted me to do a somewhat introductory talk, mention kind of some of the basics of these moduli spaces that you see in n equals 2. So, just a bit about me. Between the differential geometry and physics, I'm very squarely closer to the physics. So the aim today is more so going to be just to see how this geometry emerges from the physics rather than doing any kind of rigorous proof or anything. So as for the outline, I'm probably going to spend the majority of the time on the first bit, just going through like the basics of QFT, what is SUSY, and then we'll kind of go through and use this major tool called the IR effective action. If you guys want a more in-depth detail about this, because I won't go into full generality, there's a great lecture series by Philip Argyris and then Yuji Tachikawa. And then I'll go into more detail about an object that I'm really interested in, which is these ACI systems. And if we've got time, I'll talk about some recent inverted commas results. And by recent, I mean 10 years old, maybe. So if that's all good, I'll get going. So before I dive into the supersymmetric stuff, let me just give you some of the details about QFT in general, and then highlight why we're not really interested in the moduli spaces of non-supersymmetric QFTs. So when I have a QFT, the main objects are fields on Minkowski space, so just R13, and these carry a representation of the Lorentz group, SO13. And usually, we label these by two half integers. So this will be specified by mn in 1/2 integers. And this is just realizing the isomorphism of Lie algebras, SL2C squared, more or less, okay? So once you've specified the fields, that's telling you about the matter content of your system, and then the interactions, how the fields kind of play off each other, are governed by, dictated by an action. So if I just write my fields collectively as phi, I have an integral over space-time of some Lagrangian. And anyone who's done classical mechanics will immediately recognize that this Lagrangian is just going to be kinetic terms minus some potential. Okay? And if you want to get the energy density instead, you do a Legendre transform on this thing. Okay? So when I say moduli space, maybe mathematicians means something slightly different, but moduli space in this context is just going to be the space of inequivalent, the space of vacua of the system. So in this context, what I mean by moduli space, I call it M0, is just the configurations of fields, again, phi, such that the potential attains its minimum. Okay? And the whole goal of this system with the moduli space is to try and understand interesting physics just from the geometry of this space. So let me give you an example and then tell you why it's a really, really boring example. Okay. So if I have one complex scalar, meaning it's in the trivial representation of the Lorentz group, fine. I can consider this Lagrangian. So I have the kinetic terms. This is just a space-time derivative. And then I'm going to minus m squared, the norm squared, minus 1/2 lambda norm to the 4. And I'll take lambda to be greater than 0. Okay? So if I want to minimize the energy here, I'm just trying to kind of minimize this function. So in particular, if m squared is greater than 0, the min is just at y equals 0. It just kind of looks like a cone, more or less, right? But something kind of more interesting happens if m squared is less than 0. If you then try to minimize this potential, which goes by the name of Mexican hat because it looks like a sombrero in this case, you have that the vacuum manifold is defined by the condition that the norm is equal to minus m squared over lambda. Okay? And in particular, this is just an S1. Okay? So you have this kind of two different versions here. You have where there is one isolated vacuum, and here there's a whole continuous space of vacua. Now, I promise that this is going to be really boring, and we can immediately see that from the form of the Lagrangian. So there is a symmetry of the Lagrangian, which takes the field phi into just a U1 rotation of phi, right? You plug that in, and that's totally invariant. So what this implies is that, you know, any 2 points, say P and P prime, in the vacuum manifold have the same physics.
You wouldn't take quotient by S1? Isn't it like S1 is not like the gauge here?
Well, you see, effectively, I have this symmetry here, and I will kind of be quotienting by the symmetry, which reduces it down to just a point.
It's up to you. You can consider the system
Mm-hmm.
or not.
Yeah. So it's kind of related to what you were saying. So you have this whole S1, but because of this symmetry, you know, a symmetry shouldn't change the physics. So any point on here is related to any other just by this U1 rotation. And therefore, no matter what point I pick to be my vacuum, it's going to be the exact same physics every time. So with what you were saying is kind of quotienting by the S1, this U1 is basically kind of doing this gauging that Max was talking about. So what this is a signal of is something that physicists call spontaneous symmetry breaking. And by that, I just exactly mean I pick one of the vacua on this S1, and then it breaks this U1 symmetry because I've picked a special vacuum. But it's still really boring because all the physics is the exact same, right? You can do, phenomenologists will like this. You can do things like, Goldstone's theorem and stuff. But for our purposes, it's not that interesting. So you can kind of say, okay, is this just a really boring example and I'm kind of just leading you astray because I have an agenda and I like supersymmetry? And the thing that I kind of want to point out is that when you're working with non-SUSY theories, this is very typical. So for non-SUSY theories, M0 is typically 1, a collection of points, and so you just have some really disjoint vacua of your potential, or 2, associated to symmetry breaking. Say you have a symmetry group G, and it will break to some residual symmetry group H. So what this means for M0 is that any 2 points in M0 are going to be related by the overall action of G, but there may be this residual symmetry that it basically stabilizes any point. So M0 is just a homogeneous space for G with stabilizer H. So this means that the moduli space is isomorphic to G mod H. But again, this is you still have that action of G that relate all the vacua. And so in non-supersymmetric theories, you kind of have a really boring situation going on. And you don't really gain much information about the theory from the geometry of the moduli space.
So your example would fit into which one? Do you think about it as a point, or do you want to?
I think about it this one. U1 to the trivial group.
U1.
Yeah. And then picking the vacuum is doing that breaking for you. So you can kind of ask, why does this kind of happen? And in this example, you can see it's because I'm relating points on M0 to each other. And because they're parameterized by these scalars, this transformation is doing that precisely. So one kind of way around this is to try and have a symmetry that transforms fields into other types of fields. So maybe scalars into something like a spinor or something. And that's kind of an intuition why maybe SUSY is the way to go. So let me just outline a little bit of supersymmetry. Is that okay with everyone, just as to why it's boring? So in order to talk about supersymmetry, you have to kind of say that fields come in kind of two forms, two varieties here. So one is the so-called bosons. And these are in integer reps of the Lorentz group. Do you want me to mute that sound? Okay, I'll keep it. Okay, and if you want an example of this, like a photon, these are the force carriers of the system, typically. And then you have the fermions. And these are in half integer reps. Somebody's left now. And an example of this one is almost all the matter that you see, so electrons and things like that. Okay. And the physics of these two things are like wildly different. So the spin statistics theorem basically says that you're going to model bosons by things which kind of commute, so you look at commutators. Whereas fermions, you look at anti-commutators, thinking of them as like Grassmann odd variables. And if you want a more extreme thing, you can look up the Pauli exclusion principle for fermions. That doesn't apply to bosons and gives you wildly different physics. So what supersymmetry is just trying to do is give you some kind of equivalence between theories under the exchange of these two types of particles. So in order to do this, we want to extend the space-time symmetry group. So remember we had the Lorentz group, but we can also include translations, the R4 translations, and this is called the Poincaré group. Now you want to extend this to a superalgebra. Sorry, I'm thinking of this as a Lie algebra, just so I don't mix things up. So a superalgebra, if you're unfamiliar, is just a graded algebra. So we're going to have a bosonic part and a fermionic part. So a Grassmann even and a Grassmann odd. And we want the bosonic part to at least contain the Poincaré algebra. So we do this by including calligraphic n many fermionic supercharges. So Qi, Q bar I. So this is going to be, this is a Weil spinor. Half zero in terms of the usual labels. This is its conjugate. So it's in the other opposite chirality. Okay. And so in 4 dimensions, it's because it's a Weil spinor, these will have 2 components technically, but I'm going to suppress all of that because it's sad having to deal with all the extra indices basically.
What does including mean? You mean you look at the algebra generated by that and these?
Yeah. You have this, and you try to include these extra things, and there'll be some extra relations that I'm going to put down.
And then 1 half 0, you mean that's the degree of the sign to be generated?
This is the representation of the Lorentz group. So this is going to be I don't know, left-moving Weil spinor, and the other one a right-moving.
Telling you about some of the relations.
Yeah, precisely. Okay, so in order to kind of fully specify the Poincaré algebra, I'll give you what non-trivial commutation relations you have with these things. So you look at the anti-commutator, because remember, fermions, you look at anti-commutators. I'll say Qi, Qj. And up to normalization constants that change between references, you can make this it's just some kind of central charge. It's going to be some matrix as far as we're concerned. This is just going to measure kind of how centrally extended this algebra becomes. Then the more common one, we have Qi Q bar j. And then this goes to delta ij p. So p is going to be the momentum. It generates the translations. Okay? And if you ever see some of the quirkier supersymmetry books, it's because of this they say that SUSY is like the square root of a translation, which I don't know is the easiest way to think about it, but morally I guess that's true. Then the other commutators are kind of trivial. So P commutes with Q, and P commutes with Q bar. Okay. And that's our algebra. And for depending on how many we put in, we get a different type of algebra, basically. Yeah, sorry. So these are anti-commutators, so these will be plus, and this will be minus. Yeah, thanks for pointing that out. So the general rule is that when you have two fermions, use an anti-commutator. If there's only one, you use a commutator, and then zero. Yeah?
So here, you were thinking about it as Lie algebra now.
Yeah.
And then so what is P exactly?
So P is going to be the generator of this part of the Lie algebra. So it's going to act as like a differential operator later.
So you're just treating R4 as like maybe a Lie algebra.
Exactly. Yeah, I don't have a great notation for the like the Lie algebra version, like that kind of thing, maybe, if it's a bit clearer. Which I don't think it's clear. Okay, so let me give you an example of implementing supersymmetry. So, since SUSY is going to be an equivalence between these two types of things, if I ever specify a field, I now have to say that it comes along with like certain superpartners that are related by the supercharges. Otherwise, I don't have this symmetry at all. So what we're going to do is construct what's called a supermultiplet. So if I take n equals to 1, then the chiral multiplet is just a complex scalar and a vowel spinner, so half zero. And how are these related? Well, I can write down the relations just to be complete. You have Q, because I only have one, I'm just going to call it Q with no indices. Acting on the complex scalar is just going to give me the spinner. Similarly, if I now consider this one Q of this, well, because of this, I now have a Q squared. So if I want to implement this, then I have to try and make it equal to this central charge. But I'm going to take these to be 0, and in n equals to 1, the central charges vanish anyway. Okay? So this thing identically vanishes. Then we can also consider the opposite chirality one. This will go to 0, and then the maybe odd-looking one is that. So if you go through all the hassle of kind of like trying to compose these in every way possible, you'll find that you're always implementing these, right? You'll find that you get these anti-commute to give you that, and these commute exactly as expect. Plus complex conjugates, right? So example 2, which will be important to us, is what are the multiplets in n equals to 2, right? I won't go through the whole pain of going through it all, but I'm just going to tell you what they are. So for n equals 2, you have the vector multiplet, which contains a vector field, 2 vowel spinners, and then a scalar. Okay? So if you went through the pain of this, you'd do exactly this stuff, but now with two supercharges. And this is the vector. And then there's the hypermultiplet, which is given by complex scalar, two vowel spinners, and then an additional complex scalar. So two complexes, two vowels, one complex, one vector, right? Again, homework, do that stuff for it. It's very boring.
What do you mean you do for this diagram?
It is just roughly how they're related by the Q's, more or less, right? So if you wanted, you could think of like, I do Q1 to get this, Q2 to get that, and then I'd compose them, or it's rough, but it's just kind of a way of seeing it. Are there any other questions? Okay, cool. So now that I've told you what the content of n equals to 2 theories are going to be, I'm just going to tell you, like, how am I going to probe the moduli space? Previously, I had a Lagrangian, and I can go through the pain of writing Lagrangians down. But if you do a SUSY course, you'll learn that doing that is like a trial by fire, and it's really sad, basically. So what I'm going to do is give you an alternative kind of method, which is called the infrared effective action. So the general idea here is, when I'm thinking about the moduli space, I can think about the original theory as being defined at some high energy scale, right? A suitable energy scale where like interactions can happen and so on and so forth. So this is what's called the ultraviolet, right? And then if I want to think about the moduli space, this will kind of live at the lowest energy scale. This is the infrared, right? So what you can do is you can start by thinking about this theory and then slowly lowering the energy scale. And by doing that, you're going to hit things that, say, are they're too massive, for example, and you'll integrate them out and not treat them as dynamic anymore, because you don't have enough energy to like deal with those fields. So say these are like F1, F2 of certain masses. You can neglect them, right? What you do is then if you're integrating down all the way to the IR, you're basically going to end up with an effective theory describing the modular space. So in the non-SUSY context, you can do this and you basically get very little. You can get some information about the moduli space, but not enough. But in SUSY, because you've got these constraints coming from the super Poincare algebra, you not only have a very constrained set of possibilities, this gives rise to a lot of geometry. Okay? So let me just give you
a simple example. What would be the infrared version of circle?
Yeah, so it's difficult to kind of tell. Like, what you'll end up getting is you'll have your UV theory, which was the Lagrangian, and then you'd flow down to the IR, and you'd have the theory that is specified by any point on the circle. And usually this is what's called a sigma model. If you try to look at that sigma model and try to analyze it, you end up finding that you don't get much information about the modular space.
The QFT is not just defined by the Lagrangian. QFTs are defined by the pair, which is the Lagrangian, and the energy scale at which the Lagrangian describes the field.
Yeah.
And the quantum theory is then characterized by the path interval, which is energy over the fields that have an energy less than that number. And this integrating out is you can do part of that integral over these functionals. And that will do two things. It will lower the Lagrangian, the cutoff, and it will change the Lagrangian.
I'll also say that I haven't mentioned this, but I'm kind of implicitly thinking that everything in the UV is going to be some kind of gauge theory for now. There's subtleties that arise in specifically supersymmetric QFTs, but for now you can think of the UV thing as some gauge theory that's well defined and we know how it works. Cool. So I just want to give you an example of how SUSY restricts this thing, right? So in the IR, there's very few possibilities. You can either have a trivial theory where you've integrated out everything, basically, all of the stuff is massive and you got rid of it. You could also have an IR-free theory, which means you do have massless degrees of freedom, but they're not interacting with each other. Finally, you can have an interacting thing. This is we usually assume to be a conformal theory, but they're more difficult to deal with than the other cases. So I will kind of stick to an IR-free thing, and then I will comment later on why this is the correct thing to think about for us. So if I want to write an IR-free action for just some, like start with just some scalars, right? I could guess if I have a complex scalar, so I could guess the Lagrangian, which kind of looks like this. So Hij, I'll call this P phi I, P phi j. And the reason why I'm calling these P's is because P will act on fields just as the space-time derivative. And I'm just writing it like this so then it's very clear how these things interact with the supercharges. Okay? So I could think about this term, and then I could also think about what about the complex conjugates. So you have Hij with the bars on the indices. It's not my favorite notation, but I'll make do. And then we could do some kind of mixed thing going on. So I'll call this G, I, J bar, P phi I, P phi bar, J bar. Okay? So this is like a perfectly normal kinetic term that you could imagine being in the IR, right? But now, what if I want to implement this supersymmetry here? Well, if I just focus on this first term, and I do the SUSY variation of it. So I just act with the supercharge and see how the Lagrangian would change. You would get that if I act with Q on this thing. You find a term within this expansion that looks like this. Hij, P psi, this is now the spinor that's related by those relations over there. I, P phi j. And then you'll also get them exchanged, so I'll symmetrize the indices, okay? So this is within the SUSY variation, right? Now, if this Lagrangian is going to be supersymmetric, this term has to be cancelled by another term somehow. So I'm either going to have to add a new term here which cancels it out, or it's going to have to be cancelled by one of these, right? But now if I look at any quadratic term that I can form from these two fields, you can see that there's no possible way to cancel them out. You just write them down and you try to implement the SUSY algebra, and it's uncancelable, right? So what this implies is Hij is 0, right? By hermiticity, the bar is also 0. So what you find is that n equals to 1 SUSY forbids those two terms in the IR Lagrangian, right?
Why did we want to cancel it out?
Just because if it's a supersymmetric theory, the Lagrangian has to be invariant under the SUSY variation. So when I'm saying QL, I'm really thinking I'm taking the variation with respect to Q and then I'm subtracting the original Lagrangian in essence. So I want that variation to be 0, like the infinitesimal variation, basically. Is that okay with everyone? It's a bit, maybe a bit hand-wavy, but it's probably the simplest example. Okay? So what does this tell us about the moduli space? Well, if I think about the scalars as like belonging to some kind of manifold, then what this term is telling me is that the moduli space M naught has a Hermitian metric. G, I, J bar. Okay. So as before, we could only say that there was some, manifold, probably has a metric. Now we can say that this has, some kind of complex structure to it. Now, you can go further.
How did we get that? Because of Hij being 0?
Well, so these terms are forbidden, right? So those are gone. And the only thing that's describing your Lagrangian now is basically the derivatives of this thing, which land in some target manifold, and this metric. And then since the metric only mixes holomorphic and one anti-holomorphic, it's a Hermitian metric. So also, if you look at cubic terms, you get the following condition on your Hermitian metric. You get that the derivative with respect to phi I one second. Okay, so basically you see that this looks almost, both sides look almost the same. I've just changed indices basically, right? Oh, sorry. So you see here, I only have terms that include 2 phi's, basically. If I look at terms that include, say, 3 phi's or 2 phi's and a psi, then you could add those to the Lagrangian, for example.
Playing the same game.
Yeah.
Make a general ansatz for L with many moments summed up. And then what are the consistency conditions on the coefficients of these terms? If this Lagrangian is supposed to be very supersymmetric.
So this is not the full general form, but you could add additional terms, and also there's another type of multiplet you could add. But if you look at the cubic terms, you find this condition on G, and if you kind of reason it out what these indices mean and use the symmetry properties of G, this tells you that G can be written as the second derivative of some potential. So by the style of Poincaré lemma, basically. Right. So this thing, K, is called the Kähler potential. And this makes M naught a Kähler manifold. So effectively, when you introduce one supercharge, so one Q, you get a complex structure coming along, you get this Hermitian metric, and then if you consider all terms, not just the kinetic terms, you find that you really actually land on a Kähler manifold instead. So you've already dramatically reduced kind of the possibilities, and you've opened up, like, because of the SUSY variation not relating equivalent vacua, you've really got a rich moduli space now.
There is the argument that we can stop the considerations at cubic terms. Why do I not get infinitely more conditions the higher I go?
I mean, you could keep going, but effectively you end up getting, you just derive the same conditions. They become degenerate. I don't have a quick argument. We can maybe talk about it later if you're interested. Yeah.
Shouldn't the Kähler potential be for like the 1-1 form of the metric or the metric itself?
Yeah, I mean, I think when I'm putting the bar on the J, I'm kind of sneakily thinking about it that way. So I'm brushing things under the rug, but yeah, in essence. Yeah, thanks for the question. Cool. So what is the case for n equals to 2? So the reason why I went to the n equals to 1 case is because it's a nightmare to do the n equals to 2 case in about 5 minutes or more, So I'm just going to write down what the IR effective action for n equals to 2 is. And you get this structure. So you have the first term, which looks really similar to this one. So it's Q bar I plus Q tilde bar I j. So just to remind you, these are the 2 different scalars which are in the hypermultiplet, right? Then you have a second term that deals with stuff from the vector multiplet. So this is the scalar from the vector, the A's. And then you have a term which depends on the field strength, basically, of your vector potential. These will have no bearing, sorry, alpha, beta. This part will have no bearing on what I talk about, so I'm just going to accept everyone is okay with that, basically. So the immediate thing to note is that supersymmetry forbids any cross terms here. So this term here is totally about the hypers, and this term here is totally about the vectors. So what this tells us is that the moduli space, locally, so I'm going to restrict to some just patch, let's say, is described by a part which is only about the hypers and a part which is only about the vectors. Okay? If I change my patch U, these things will also change. So there's kind of secretly a dependence here on U, right? Now, what you can do is you can also say, well, let me neglect the hypers. I can set all these fields to be trivial, basically, and only consider the vectors or vice versa. And in doing so, you get special parts of the moduli space.
So the metric is reducible locally, right?
Precisely.
But
Yeah.
if the metric is locally reducible globally, it's also at most of vibration. The holonomic will reduce.
Yes. So the problem with the moduli space for n equals 2 theories is that they're quite singular spaces. They look a bit odd, so the whole space might not be some kind of nice, smooth manifold. But what this local thing is saying is that there's a patch that always has like hypers dynamics and then vector dynamics, and they kind of talk about that. Cool. So if I trivialize the vectors first, so I'm totally neglecting this part, right? Then MH is the Higgs branch. Okay? So you might have heard of this before. What is the effective theory on the Higgs branch is just the first term, right? So this is what's called an n equals to 2 nonlinear sigma model, right? And if you are familiar with the work of Alvarez, Coulomb, and Dan Friedman, they analyzed precisely these theories and what the consequences of supersymmetry are for the target space. So previously, when we had this kind of thing, we had one supercharge and we got one complex structure. Now we have two. So you can say, okay, maybe I have two complex structures, but I could also multiply them both together, so Q1, Q2. What this does is like this gives this part of the moduli space three independent complex structures. So MH is a hyperkähler manifold. Right? Which is just precisely, the definition that I just said. Okay? And one important thing about the Higgs...
Can you see that? We just argued up to the fact that the product is Kähler, right?
Yes, so what I'm trying to do here is I'm not trying to look at the full space anymore. I'm just saying, okay, I neglect these terms, I go to the submanifold, which is only governed by hypers. And now I only have this part of the effective action. And if you repeat the analysis that we did just for the n equals to 1 stuff with effectively, with two complex structures, and then you generate the third by multiplying them, you end up finding the exact same results holds, and you get a hyperkähler manifold. So one of the important things which I'll just mention is that the hyperkähler metric on this space is, it's impervious to quantum corrections. So it's protected by supersymmetry, and you can do everything with that classically. You don't have to worry about adding additional terms from quantum effects, basically.
So it's really hyperkähler, not like a proxy.
No, this is, genuinely hyperkähler. This is protected by supersymmetry. So if I now, if I trivialize the hypers instead, then we get that MV is the Coulomb branch. Okay. So we could try to play the same game as that we did just then. We cover up this part of the action, and we just look at that part. And what are the consequences for the geometry? So one of the conditions that we get is you get this thing. Which looks really similar to what we had for the other thing. So first thing to note is that the Kähler metric is now played by the imaginary part of tau alpha beta, just precisely kind of this part. And then an additional constraint is on this thing, and tau is going to be a holomorphic form. So this is not the exact same as the Kähler condition here. And if you reason that with the indices and you note about the symmetry properties of tau, you then get another form of the Poincare lemma, basically. So you're now finding that tau alpha beta can be written as the second derivative of some holomorphic potential. So again, it looks very similar, but there's bars here, there aren't bars there. And this thing is called the pre-potential. Okay. And the pre-potential has like special importance in n equals 2 theories. It basically fully determines the Lagrangian, and you can write a lot of things in terms of it. So a manifold with this precise structure is called a special Kähler manifold. Cool. So unlike the Higgs branch, the metric on the Coulomb branch can actually receive quantum corrections. So it's not impervious to these corrections, but it's never fully lifted. You always end up with some Coulomb branch. You don't lift the full thing. But nonetheless, there's certain properties by the Coulomb branch that makes it very amenable to study. One of which is, as of right now, there are no interacting 4D theories that don't have a Higgs branch, Coulomb branch. I.e., they are, they have at least a complex one-dimensional Coulomb branch. And this is not the case in other dimensions. The analog of the Coulomb branch in 3D, you can very much find theories that interact but don't have a Coulomb branch, even with the same number of supercharges. Cool. So that's kind of the main definitions, the main things I want to get through, just like why the physics gives you these manifolds, basically. And now in the last 15 minutes, I just want to mention a consequence of this special Kählerness, right? So two ACI systems. Okay. So if I'm sitting at any point on the Coulomb branch, what is the physical data that I have access to, right? I have access to this tau alpha beta, which is nominally playing the role of our metric. So you have the data. Tau alpha beta. What else? You actually have a lattice of charges. So you can talk about the electric and magnetic charges of your theory, and on general grounds, you can argue that this is just going to be a lattice of rank 2R, where R is the dimension of the Coulomb branch. Right? So for each dimension, there's one electric and one magnetic charge. Right? You have access to that at any point in the Coulomb branch. And then finally, something maybe a little odd is you have an antisymmetric pairing between electric and magnetic charges. And this is just called the Dirac pairing. So the Dirac pairing measures like the mutual non-locality of states. So whether or not one state can detect another just by, say, encircling it in moduli space, for example. Right? So at any point on the Coulomb branch, you have this information. You can ask, what kind of stuff can you cook up from this, right? And there's quite an obvious one, which is you can form a complex torus. X c to the r modulo this lattice. But how am I embedding this lattice in there? Well, I use tau alpha beta here. So I have some kind of base. Basically, I have a basis for c to the r, and I want to write the basis of the lattice in terms of these basis vectors, or vice versa. And so I can choose the first part of this basis change matrix to be diagonal, right? And then I complete it with this thing. So this is just gonna, again, this is just gonna tell me how the basis of gamma here relates to the basis of c to the r. And this explicitly defines what this quotient means, right? So this is just a complex torus. Now, what does the Dirac pairing get us? Well, the Dirac pairing makes this complex torus into something called an abelian variety. So what is an abelian variety? It's just a complex torus which is also a projective variety, right? And you may ask, why does an antisymmetric pairing do that for us? Well, the Dirac pairing J should really be thought about as like the first Chern class of an ample line bundle, right? And this ample line bundle, the sections of it are going to tell you how to embed it into projective space. So at any point on the Coulomb branch, you can kind of form this thing. But I've maybe told a bit of a lie, and the lie is really when I said any point. So at any smooth point, you can associate, you can take a point in the Coulomb branch and define an abelian variety, right? I haven't mentioned this, but you know, the Coulomb branch in essence could display metric singularities. This is something I kind of brushed over because I'm secretly thinking about gauge theories at first, but now in full generality, you can have codimension 1 singularities for the metric, right?
So A is a point
In the Coulomb branch.
Coulomb branch, and that gives you, and then how do you define XA? What does A give you that those info? Yeah.
XA will be this, yeah. So at any smooth point, you get an abelian variety, but then on the non-smooth points, the points where you have metric singularities, you can't quite get a full abelian variety. In other words, this period matrix won't give you a good quotient, effectively, right? But nonetheless, you can look at how those abelian varieties kind of degenerate as you go towards the singularities. So instead of just some kind of product of abelian variety and base or some kind of fiber bundle, this ends up giving you the structure of a fibration, say pi from, I'll call it script x, to the Coulomb branch, where pi inverse of A is generically an abelian variety, okay? Now, what else can we do with this? Well, if I want to try and claim that this construction gives me some kind of interesting physics, I want to be able to kind of get back to these nice coordinates I had, right? These A's, which are called the special coordinates. So how can I recover it from these abelian varieties? Well, I can define a holomorphic 2 form. Omega, so this will be holomorphic 2 form on the total space. And I'm going to try and recover the special coordinates dA from some kind of fiber integral on the abelian variety. So omega, and then this will also give me a set of dual variables. Okay, so what are all these things? So alpha and beta are a symplectic basis of H1 of the abelian varieties, right? And what I really need to do is I need to try and make sure that I get like the correct dependence on the base coordinates and on the fiber coordinates. So really what I should do is I should make it so omega vanishes if I purely restrict it to the fiber. This just is going to make sure that the once I've done the fiber coordinates, I've got well-defined coordinates on the base without thinking about the variety, right? And then basis of H1.
Which means you have Lagrangian fibration.
Precisely, right. And why is this the natural way to get A in A dual? Well, when you have these singularities in the Coulomb branch, If you encircle one of them, you get something called an electric-magnetic duality. So encircling one of them will change how you define your electric and magnetic charges, right? This is something that you don't even have to do any of the geometry to get. You can see it, in books by like Tachikawa, for example. It's a very easily digested thing. But now, if I do this in this context of this geometric application, going around these singular points of the vibration is going to give me a monodromy in the H1, basically. So the monodromy in H1 is going to precisely give me those EM dualities, right? So this is kind of at least an intuitive reason why this should work, right? Now, altogether, this holomorphic two-form that makes it Lagrangian, the abelian varieties, and the polarization, this gives this vibration the structure of an ACI system, algebraic completely integrable system. Okay. So you may ask, what does this have to do with integrability at all, right? Well, this is like a generalization of like the phase space of an integrable system. The Coulomb branch I think of as like the constants of motion. They're in involution with each other, and the fibers are tori. So this is kind of like your action angle variables, right? So what this is saying is that to every Coulomb branch of a physical theory, I can associate an integral system which encodes the physics, right? Is that okay? Cool. And then with the last 5 minutes, I'll just give you an application of why these systems are so useful for us. So if I now impose a conformal symmetry, what this does is now it means that the Coulomb branch is going to be scale invariant, right? I now have an action of C star on the Coulomb branch, and all physics should be invariant underneath it. And I'm also going to take the dimension of the Coulomb branch to be 1. So I have this picture for the ACI system. I have the Coulomb branch, and over a generic point, I have a one-dimensional abelian variety, which is everyone's favorite, an elliptic curve, right? I now can say, okay, I told you that there were some non-smooth points. Where does it belong? Well, now that I have the C star action acting on this thing, I can only have one, and it has to be at the origin, right? So what kind of structure is this? This is telling me that in rank 1 conformal theories, it's just an elliptic vibration. Right? So the geometry of elliptic vibrations are basically going to tell you all you want to know about the rank 1 theories. So if I call this E tau, this is just an elliptic curve. I now can ask, what are the possible ways of fibering an elliptic curve over a disk with some singular points? And I kind of promised recent results, and this is very recent to me, 1963. Right? Kodaira classified these. More precisely, he classified the possible singular fibers, right? So what are the possibilities for us? If we want to make sure we keep scale invariance, we get 7 possibilities. And this is the notation that's in their papers, I believe. So you have one called type 2, 3, 4, I0 star, 4 star, 3 star, 2 star. These are just some labels. I'll explain maybe what they mean in a sec. And then if you want more geometric understanding, you can associate a Dinkin label to each of these as well. So you have, this is affine E8, affine E7, affine E6, D4, affine A2, affine A1, and trivial diagram, right? What do these tell us? Well, they're just telling us that if I go to the singular point and I resolve the singularity that I get, this is exactly telling us the structure that we get. So we blow it up a certain number of times, and you get a certain number of P1s intersecting in the shape of this thing. So if I take the example of the 4 star, I move to the singular point, I get some mess, I blow it up, and I get something which looks kind of like this. So this is a P1. All of the lines are drawn are P1s. 5, 6, 7. And if you note the intersections, it gives you precisely an affine E6 diagram, right? So you may say, I have 7 geometries, right? These are the scale invariant ones. The other ones Kodaira classified aren't relevant for us. There are 7 rank 1 theories, right? No, it's never that simple, unfortunately. So,
Sorry, why are there only those in Kodairas computation?
yeah, so Kodaira has these other infinite series, right? The I zeros and the I stars. Those additional ones, so I can put them in here, just to IN star. If you look at what they would mean physically, is you don't actually find you have a scale invariance in this sense, right? You find that you have like a kind of cusp singularity, and this tells you about some kind of IR-free thing. So you don't find the conformal symmetry that you want, but they do appear in non-conformal theories.
Your complex structure of T2 needs to be a homogeneous.
Well, not always. In the case of I0 star, it can be anything.
That is true.
Yeah.
But
It would be infinite here. It would go to the weak coupling point of the I infinity, I guess, in the fundamental domain. Right. So just in the last minute, to get the physics from this, you need to give some extra information, and that extra information is the flavor symmetry. So what do I mean by flavor symmetry? It's just telling me that there might be some additional global symmetries that the geometry doesn't account for just from this classification. And the way that you can incorporate it, again, in a geometric way, is by thinking about how you can deform these different singularities into each other. So if I think about, say, the 2 star, I draw it like a cone, because you can think about all these as kind of a cone. And you want to say, how can I deform this to split it into different lower type singularities? So I can kind of think about the obvious one, which would be I go to a 3 star, right? And then this will turn out to be an I0 star. And then the kind of physical intuition, kind of the physical mechanism which will do this is I've introduced a deformation parameter. Call it M, right? What I'm doing here is I'm saying I have supported a certain amount of global symmetry here, and I can turn on some kind of deformation to break that symmetry, right? And in doing so, I've split it off in a certain way. And I can take this M to infinity, and I can recover this conformal one. So I can get this theory now. But I could, in theory, do it a different way, and I could split it off and using different forms of these things. And that would just tell me I've got a different global symmetry here, and I'm breaking it in a totally different way. And that's pretty much it. So thanks for listening.
thank you very much. We had questions along the way, but are there any more questions?
Yeah.
And then just like a reference for this stuff.
Yeah. So if you want the basics for the QFT, like the actual physics, Tachikawa has a book from 2013. N equals a 2 for pedestrians, I think it is.
I think I'm more interested in like just the geometry first.
Okay, well then, if you want the IR effective action stuff that leads to the geometry, there's a set of lecture notes by Philip Argyris from 1998. They're available on his website. And then if you want to kind of look more into the actual physics, the actual geometry, there's various reviews by Donaghy in the late 90s, and there's also some reviews from the last 5 years by Mario Martone and various summer schools he taught at. Like there's a big compendium by, I think like Mohammed Akond is on one of them. Cool.
So you mentioned the hyper-Kähler metric would appear naturally and Kähler metric would appear naturally. I've never seen moduli space would have Claviau, non-hyper-Kähler Claviau or G2 or any other interesting geometries. Is there any hope or way or reason that this would never happen?
So at least in the n equals to 2 case, you saw that there just wasn't enough supersymmetry to give you, like, to basically reduce the holonomy group even further, right? In theory, you can get even more supersymmetry. You can do n equals to 4, but then that, like, basically totally determines what the moduli space is. So for when you have an n equals to 4 theory, you actually find that it is the whole moduli space is C to the 3r modded by a Weil group, right? So it's completely determined there. But then if you go into supergravity and you allow even more supersymmetry, then you get structures that I'm not really aware of, and maybe there you can get something a bit more spicy, let's say. Basically, once you get to n equals to 4, that's when I stop caring, because then you get gravity involved and it gets a bit more complicated.
But even from like completely abstract point of view, do you know any example that some other holonomies would appear?
No, not that. I mean, unless it's just some coincidence, I don't know, basically. I think the best that we've got is this hypercalar, basically. Which, I mean, you know, it could work out. I just don't know.
Okay. We have no further questions.
Any questions?
No, everyone's left. Everyone's left.